again. My name is Suleimanov. We'll be talking about radiation properties in magnetic stars. So we'll continue the previous session. Now, yes, now probably we're going to get some real details.
Thanks. I would like to present this work, which recently performed in collaboration with all of these my co-authors. Outline of my talk is this. It's a very short presentation, will be, I hope. And
oh, sorry, we don't do those at this meeting.
Good. So the motivation is here. So my aim is possibility to obtain neutron star radii, which is very important for equation of state in core of neutron stars. So I think it's very clear for all of us. It's not necessary to explain very much. And my intention is I will speak about magnification 7. It's X-ray dim isolated neutron stars. It's 7 in our galaxy. They was discovered by Rosat. So X-ray emission from isolated neutron stars is in the 6 of between 7 isolated neutron X-ray dim. So I will say isolated neutron star. It means that magnification 7 only, not pulsars and so on. So for shortly. In the 6 objects there are absorption lines with it can be significant equivalent width up to 200 equivalent electron volts and the temperature of about less than 1 million Kelvin, and we believe that magnetic field on this isolated neutron star surface of about 3 times on 10 order 13 Gauss. It's possible to obtain from this absorption line if they will be interpreted as proton cyclotron lines, or if we put some of the objects in PP dot diagram. This in this kernel, it corresponds to of about few 10 order 13 Gauss again. So there is some other interpretation of these absorption lines. Here I will speak about, I will use assumption that a magnetic field on the isolated neutron stars is of about few on 10 order 13 Gauss. So other possibility, it's one I reject for short. But it's possible to discuss, of course.
You said on the previous slide that the P dot there, that in 2 cases there is agreement roughly with the B field. What about the others? Do we have P dots? The others?
I don't remember details exactly. So it's possible to find.
It's kind of interesting if they're not too bad or if they're terrible.
So, all of these isolated neutron stars have significant from 1% to up to 20% positive fraction. So there is like changing of brightness. Most interesting case is this RBS 1223 because there is 2 maxima in the light field, which correspond to poles on the neutron star surface. It's interpretation of course. And these poles can have different temperature and different size on the neutron star surface. So, it's some movies for 2 poles on the neutron star surface. And what's the origin of this hotspot on the neutron star surface? If you take normal core dipole distribution for magnetic field, in this case, temperature distribution will be smooth enough. It's not necessary, not enough to reproduce this large pulse fraction in the observed light curves. So normal dipole magnetic field distribution creates temperature distribution which can give only about 5% in the best case of pulse fraction in light curves. Therefore, we have to impress some other mechanism for difficult temperature distribution with bright spots on the neutron star surface. There is two possibilities in principle. First is the bright spot which rising due to pulsar mechanism, due to relativistic particles which hit the polar caps on the neutron star surface. But periods is very long, and therefore size of this spot must be very small, not less than 1 degree. So it will be a very small radiated surface, and this is related to the stars must be very close to us.
Why is that? Why do you need one degree only?
Because its period is very long, so light cylinder is very high, and lines, magnetic field lines, which will be very close to pole. Okay. The second possibility is non-usual magnetic field distribution in the neutron star crust. For example, it can be a case when all the external colloidal magnetic field, but inside of the neutron star crust, magnetic field concentrated in the crust only, not in the superfluid, superconductive core of neutron star. In this case, in the crust, magnetic field is along the neutron star surface, and heat transport across this magnetic field will be difficult. So most of the energy will be released in the hotspots at the magnetic field poles. And other possibility, some toroidal component in the crust, in the some difficult approximations, force-free, for example. Force-free approximations for toroidal component give a strong toroidal component on the neutron star surface too. Not only dipole magnetic field on the surface, but strong toroidal component too. And in this case, we can obtain this kind of temperature distribution. This taken from paper.
If we work on these models, know that we have the superfluid phonon transport that Sanjay described. So this toroidal field may have
okay, it's
I don't know
complicated, I think, models, and I'm not a specialist in this.
Yeah, I don't know how much is resolved with it.
So it's for illustrative purpose. Yeah. So there is theoretical model which can explain small bright spots on the neutron star surface. If people use some approximation assumption about magnetic field distribution in the neutron star crust. Okay, so it's for example, it's for classical dipole magnetic field temperature distribution along the surface this magnetic latitude. So it's poles, it's equator, magnetic equator, and what we can obtain using some different models: bright spots, small size, cold equator.
I mentioned it because you get that at all and the at paper.
Okay.
So I'm shooting my feet, but
sorry. So, main problems in comparison with observations. What kind of local models of highly magnetized neutron stars can provide observed equivalent width of the absorption features? And what distribution of effective temperature and magnetic field across the neutron star surface we need to explain the observed pulse fraction and the width of the absorption feature? So, limiting case here is star, isolated neutron star, radius 1223, because equivalent width is of about 200 electron volts, and pulse fraction is very high, about 18%. So it's a problem which I try to resolve in my presentation here. So we used 3 different local models of neutron star surface. Semi-infinity plasma with atmosphere. We can consider it only hydrogen partially ionized model atmospheres with vacuum polarization taken into account. And the second, thin hydrogen atmosphere above condensate iron surface, or naked condensate iron surface. For example, we used this approximation for spectrum of condensate surface divided from Planck function. We can compare this approximation with graphic which Alex Patikin shown before. So it's some dumping and so on. So it's very crude approximation only. But we believe that its approximation can give us some basic knowledge, basic results about integral spectrum of relating to stars if we use this approximation. And then we use this approximation for calculating of thin hydrogen atmosphere above condensate iron surface, and use these radiation properties as a low boundary condition for radiation transfer in model atmosphere calculations. So this a little bit about hydrogen model atmospheres. I will skip it because Alex discussed it very good in previous talk. So it's results. Emergent spectra. So emergent spectra for hydrogen atmosphere above black body, so using black body as low boundary condition. In this case, we have this proton cyclotron line and some additional absorption due to bond transitions in atomic hydrogen. If our atmosphere is thin, therefore this absorption, additional absorption feature is small, and here is larger for this surface density. And I would like to say that semi-infinity model atmospheres gives the same, very close energy spectrum as here for this surface density. And if we used condensate iron surface as low boundary for model atmospheric calculation, in this case we obtained additional strong absorption feature due to this feature. Its feature arising because between these energies only one mode can propagate in the condensate iron surface. So its emissivity 2 times less than normal black body here, for example.
And another one is just, well, it cannot propagate, yeah?
Yes.
It is,
So it's possible, therefore, to approximate this emergent spectra by black body, some diluted black body maybe with temperature different from the effective temperature, and additional 1 or 2 absorption futures with can be approximated by Gaussian line. The first, of course, is proton in the place of proton cyclotron line. It's for simplicity. It's possible, of course, Alex showed us that it's possible to calculate model atmospheres, a lot of model atmospheres, and calculate the integral spectrum of the isolated neutron stars using many emission spectra from local points on the neutron star surface. And it's possible to use some other approach to, I think, for the first step, to understanding what kind of local model can operate in the real object. It's possible to take this simple approximation, then we will calculate any integral local spectra very fast. So, okay, we used this, and I would like to remark that here in the model atmospheres, equivalent bits of this absorption feature of less than 100 electron volts. In the condensate surface, it's of about 150 electron volts, and in the case of the thin hydrogen atmosphere above condensate iron surface, this equivalent bits of this absorption features is more larger than some of the naked surface and hydrogen atmosphere, because there is some interaction between low boundary condition and radiation transfer in the atmosphere. So you can see that this equivalent bits, in principle, incomparable with observed equivalent bits in the spectra of isolated neutrons. So we used this simple model.
Valer,
Yeah?
probably it would worthwhile to mention that this coefficient B nu at the left is, corresponds to some effective, to not the exactly effective temperature.
Yes, it's some color temperature.
Yes.
In real, so for simplicity, I used later this.
Lev, can I ask you about the
Yes.
previous graphs too? You have this one broad line on the right graph, and then a cyclotron line absorption, very narrow. So what is the equivalent bit on the right?
Here,
Yeah, there is one broad absorption line because of this effect of the
it's of
condensate.
about 400.
So it's, but this
It's,
narrow
it's
line,
the sum, this and this.
but then it's
The-
split.
I calculated this equivalent bits using this approximation of continuum, this
Mhm.
thin black line. So from here up to here.
So this is the sum of those two.
sum of the, so as single. So most of the equivalent bits from this broad feature. So, model for calculation of isolated the stars to bright, not spots, bright region around magnetic field, gravitational redshift and line bending taken into account, and we use this kind of approximation formula for temperature and magnetic field distribution along magnetic field, across magnetic field surface. So there is one parameter, A. It's approximately square root from ratio of toroidal component to poloidal component on the magnetic field, so on the neutron star surface. A equal 1/3, 0.25. It corresponds to fluid dipole, classical dipole length. So, and for detailed calculation, we used 3 temperature distribution, 2 bright spots on the poles with size 5 degree. Then classical temperature distribution from co-dipole model. And in these two cases, the magnetic field distribution is dipole magnetic field on the neutron star surface. And third distribution with strong toroidal component, this small bright sizes hot region on around magnetic poles. And of course magnetic field distribution has strong toroidal component. And and we calculated integral spectra for this three temperature distribution using hydrogen model atmospheric approximation, then naked condensed iron surface, and then thin hydrogen atmosphere above condensed iron surface. And these colors correspond to this temperature distribution, legates of the lines. It's interesting that in integral spectra, equivalent width is the same, approximately the same as in local spectrum. It's very easy to understand this. There is good analogy with fast rotating ordinary star. And in non-rotating stars, some absorption lines has some equivalent widths and very narrow and deep, for example. In fast rotating star, due to Doppler effect, this absorption line will be wide and shallow, but equivalent widths will be the same. The magnetic field distribution across neutron star surface works in the same way. It's shift position of the absorption feature. Therefore, it's wider and shallow, but equivalent widths will be the same. Close to the same, approximately the same. So, and we, for example, this dotted line and magenta line here, it's calculation for two different local absorption features with about 100 local equivalent bits and of about 20 electron volts for this. You can see that's very shallow but very wide absorption feature with small equivalent bits. So, most interesting case of strong toroidal model with strong toroidal component. You can see here this compare emergent spectra with absorption feature, dashed line, and without thin solid line. If you don't know that there is absorption feature, we cannot to say from observation that there is absorption feature. But we see in the observed spectra of isolated neutron stars absorption feature. It's very good observable. Therefore, we can make conclusion that there is no strong toroidal component of the magnetic field on the surface of isolated neutron star. And most significant equivalent is for thin hydrogen atmosphere above condensed iron surface. For limiting case, RTS 1223, where observed equivalent width is comparable with this value. Therefore, we can say that we need a thin hydrogen atmosphere or some light element atmosphere on top of condensed surface to explain the observed spectrum of competition serum. So, that's all.
So, to go back to, I guess, Danny's question, comment, if you remove the link between the magnetic field and the surface temperature distribution, then the result that you rule out, the toroidal component is weaker. So if you remove that link, how does that affect the final conclusion?
So now we perform the second part of this work for fitting of the real data spectra and light curves of RDS and in this case we in real take toroidal type of magnetic field and temperature distribution with small size bright spots. So it's necessary to explain high pulse attraction and observed absorption feature.
So would be not self-consistent, but nevertheless it will be a good idea. Well, it will show what you need.
Yes. But there is a model which published in a previous paper of Geppert control in 2004, where they considered magnetic colloidal only magnetic field concentrated in the crust only, not in the core. In this case, it's possible to obtain relatively small hot regions around around magnetic fields and external dipole magnetic field.
Yeah, but the same comments will be applied to that paper. The absence of superfluid comments.
So,
We just have to decide that since Sanjay is not here, we don't trust his calculation. We can just have a vote now and say, well, you're not allowed to talk about this anymore.
so it's in any case it's necessary to move in from the both directions, from observations, what we need to explain, and from the second direction from theory.
Well, I think we're learning, not just here, but we're learning all the time that when we put more details into our models, things tend to balance or smear out and remove things. You have a promising idea and suddenly it's completely wiped out by some other mechanism. And so you can take the view that this is a disaster, that we will never learn anything. But, or you can say, well, actually, we're improving all the time. It's just a bit unfortunate that there's these counterbalance and reality is a little bit complicated. I don't know. We just have to work down this list of things that we should do, and 200 generations from now we'll succeed. Probably, maybe. We will not succeed.
Let me ask you the same question I asked before. What do you expect the magnetosphere to do and influence your results?
I didn't investigate this question.
But I mean,
So,
just if you know, back of the envelope test. Do you expect
magnetosphere, you mean some particles in the magnetosphere,
Sure.
or only magnetic field?
No. Partly. I mean, I'm really thinking about you're shooting photons, and you want to know, how their propagation would be affected by the fact that they won't reach immediately the circuit. They will first have to scatter through the charge distribution in the magnetosphere.
So it depends on the optical thick of this magnetosphere. If it's very small, in this case it's no problem.
Right.
But we know that for magnetars there is resonance scattering in the magnetosphere. So photons in some distance from neutron stars, where the electron cyclotron resonance will be in this energy band where most of the photons radiate, it's possible to create some power law tail for the spectrum.
So you're saying
So
it could have.
But this power tail is not observed in the spectra of this radiating star.
On the other hand, magnetars probably rotate slowly, so the magnetosphere is.
It's comparable layers, I think.
Pretty much the same.
Yeah, these are also very small details, which means that the magnetosphere
Very, very small, charge density. Yeah.
Thank both our speakers. And seeing as we've decided to be lazy, enjoy yourselves. But don't forget that we've decided to end this program